Hello Vivians, I am Lakshmi Narayana. Today our concept is functions. What is a composite function? Let us take two functions f from a to b and g from b to c. Then g composition f from a to c defined by g composition f of x or g circle f of x is equal to g of f of x for all x belongs to a is called composite function of f and g. This is a diagrammatical representation of composite function. Let us take an element x in A, f from a to b is a function, then f of x equal to f of x represent in b, then apply function g to f of x, then that is g of f of x. Totally the function f from a to b and g from b to c. It goes to g circle f from a to c. For example, let f from set 1 3 4 to set 1 to 5 and g is a function from set 1 to 5 to set 1 comma 3 is given by f equal to set of ordered pair 1 comma 2 3 comma 5 4 comma 1 and g equal to set of ordered pair 1 comma 3 2 comma 3 5 comma 1. Now we have to find g circle f and f circle g. Here f of 1 equal to 2, f of 3 equal to 5, f of 4 equal to 1 and g of 1 equal to 3, that is this one, g of 2 equal to 3, that is g of 2 equal to 3, g of 5 equal to 1, that means g of 5 equal to 1. Now g circle f of 1 equal to g of f of 1 equal to g of f of 1 value 2. So substitute in place of f of 1 equal to 2, that is g of 2, g of 2 equal to 3, therefore g of 2 equal to 3. That means g circle f of 1 equal to 3. Now g circle f of 3 equal to g of f of 3, that equal to g of f of 3 value take from here. F of 3 is equal to 5, so in place of f of 3 substitute 5, therefore g of 5, g of 5 equal to 1, g of 5 equal to 1. Now g circle f of 4 equal to g of f of 4, that equal to g of 1, that equal to 3. Therefore g circle f equal to 1 comma ordered pair 1 comma 3, ordered pair 3 comma 1, ordered pair 4 comma 3, that is g circle f. Similarly f circle g equal to 1 comma 5, 2 comma 5, 5 comma 2, that is a set of ordered pair 1 comma 5, 2 comma 5, 5 comma 2. If we see g circle f and f circle g, here g circle f is ordered pair 1 comma 3, 3 comma 1, 4 comma 3. Here f circle g is 1 comma 5, 2 comma 5, 5 comma 2. From these two conditions, g circle f is not equal to f circle g. Therefore, always g circle f is not equal to f circle g except f equal to g. Now we will see one more example, that is if f from R to R, g from R to R are two functions defined by f of x equal to 3x minus 1, g of x equal to x square plus 1, then find f circle g of 2 and g circle f of 2x minus 3. Here f circle g of 2 equal to f of g of 2, f of g of 2, here g of x is x square plus 1, so g of 2 is 2 square plus 1. So in place of g of 2 substitute 2 square plus 1. 2 square plus 1 is 5, so f of 5, f of 5. Here f of x is 3x minus 1, so f of 5 is f of 5, in place of x substitute 5, 3 into 5 minus 1. So here 3 into 5 minus 1, 15 minus 1, 14. Therefore f circle g of 2 is equal to 14. Similarly, g circle f of 2x minus 3 equal to g of f of 2x minus 3, g of f of x is 3x minus 1. So f of 2x minus 3, in place of x substitute 2x minus 3. So 3 into 2x minus 3 minus 1. 3 into 2x minus 3 minus 1. So 3 into 2x 6x minus 3. 3 into 2x 6x minus 3 into 3 9 minus 1. So 6x minus 10. That equal to g of 6x minus 10. Now substitute in place this 6x minus 10 in the function g of x. Here g of x equal to x square plus 1. g of 6x minus 10 is 6x minus 10 whole square plus 1. Its value is this one, 36x square minus 120x. Here 10 square is 100 plus 1 101. So g circle f of 2x minus 3 equal to 36x square minus 20x plus 101. Here we have to observe 3 points. That is, if f from a to b, g from b to c are two functions, then g circle f from a to c is also, f from a to b, g from b to c are two 1 functions, then g circle f from a to c is also 1. In the same way, f and g both are two onto functions, then g circle f from a to c is also onto. In the same way, if both are 1 and onto, that is, if both functions are bijective functions, then g circle f from a to c is also bijective function, that is bijection. Now we have to prove these conditions. Children, all of you listen carefully. If f from a to b, g from b to c are two 1 functions, then g circle f from a to c is also 1. Here f from a to b is 1 function. That means f from a to b is a function. So for x1 comma x2 belongs to a, f of x1 comma f of x2 belongs to b. And g from b to c is 1 function. That means it is a function. For f of x1 comma f of x2 belongs to b, then g of f of x1 comma g of f of x2 belongs to c. Suppose g circle f of x1 equal to g circle f of x2, that is composite mapping. That implies g of f of x1 equal to g of f of x2, f of x1 equal to f of x2, because g is 1 function. What is 1 function? Working rule. 1 function working rule is, if two functions, if a function is 1 function, suppose here g is 1 function, that implies g of y1 equal to g of y2, that implies y1 equal to y2. In the same way, g of f of x1 equal to g of f of x2, that implies f of x1 equal to f of x2. Here f is 1 function given in the given condition, the statement f is 1 function. So f of x1 equal to f of x2, that implies x1 equal to x2. Finally, g circle f of x1 equal to g circle f of x2, that implies x1 equal to x2. Therefore, g circle f is 1 function. That is, g circle f from a to c is 1 function. Now we will go through the next concept, that is proving onto function. If f from a to b, g from b to c are two onto functions, then g circle f from a to c is also onto function. Now we have to prove. Let us take any arbitrary element z in the set C. Z belongs to C. G is a function from b to c is onto. Then there exists y belongs to b such that g of y equal to z. The same way here, y belongs to b is taken. Y belongs to b, f from a to b is onto. That implies there exists x belongs to a such that f of x equal to y. These two conditions are onto function conditions, onto function working rules. Now g circle f of x equal to g of f of x. G of, here f of x equal to y, substitute f of x equal to y. Now g of y, here g of y equal to z, that equal to z. Therefore, g circle f of x equal to z. For z belongs to c, there exists x belongs to a such that g circle f of x equal to z. That only we wrote here. Therefore, g circle f from a to c is onto. Now we will see the equality of functions. If two functions f from a to b, g from c to d are said to be equal, if a equal to c, that means domain of f equal to domain of g, and codomain of f equal to codomain of g, that is b equal to d, and f of x equal to g of x for all x belongs to domain of f. It is denoted by f equal to g. Here, some mathematicians told that two functions f from a to b, g from c to d are said to be equal if a equal to c, that is domain of f equal to domain of g, and f of x equal to g of x for all x belongs to a. Here above said that both domains equal and codomains equal, and f of x equal to g of x. Here, if domains equal enough, then f of x equal to g of x, then we can say both functions are equal. Now we will see one example. On what domain the functions f of x equal to x square minus 2x and g of x equal to minus x plus 6 are equal. On what domain these two functions are equal means we have to find the values of x, because x is only the domain values. So we have to find x value by making these two functions equal. Taking f of x equal to g of x, f of x value x square minus 2x and g of x value minus x plus 6. X square minus 2x, send minus 2x to left side, plus 2 minus x left side, plus x. That means minus 2x plus x is minus x, plus 6 left side minus 6. Therefore it is a quadratic equation. By factorizing you will get x minus 3 into x plus 2 equal to 0. That implies x equal to minus 2 comma 3. Therefore the domain values are minus 2 and 3. Therefore f of x and g of x are equal on the domain minus 2 comma 3. Now we will see one associative property on three functions. If f from a to b, g from b to c, h from c to d are three functions, then h circle of g circle f equal to h circle g circle f.